All right, guys, so we're up to slide 23 of the Chapter 3 PowerPoint. We've introduced the mole map, we've looked at balanced equations, so now we're going to start working problems that relate chemical equations and mole ratios. So, I have a reaction, hold on, it's at the top. I have a reaction, 2 magnesium atoms will react with 1 oxygen molecule to make 2 MgO formula units. Now again, I want to actually look at that reaction in terms of mole ratios. So it's going to be 2 moles of magnesium with 1 mole of oxygen to make 2 moles of magnesium oxide. That's kind of the best way to look at the reaction. So if I look at this first question, how many moles of MgO will be formed when 7.5 moles of O2 react? So again, I'm going to get my board out and start working. So let's just look at that question. I did not plan ahead very well, so I got to clear my board real quick. All right, so for this first equation, first problem, I have 7.5 moles of O2, and I want the moles of MgO. So, when I look at this, I have to have my balanced equation up top, 2 Mg's plus O2 yields 2 MgOs. And as long as the equation has already been balanced, that means that all the ratios have already been determined. I know that it's a 2 to 1 to 2 ratio between all of them. But when I look at a problem, I'm only going to focus on the 2 things that are mentioned in the problem. Okay? So, I know that I'm using O2 as my starting point, and I'm using MgO as my answer. So I need a ratio just between those 2 things. O2 to MgO, O2 is going to go in the bottom, MgO is going to go in the top, and I look at the ratio in the balanced equation, 1 O2 reacts to form 2 MgOs. So 1 to 2 if I just focus on those 2 compounds. So 1 O2 reacts to form 2 MgOs, and specifically it ought to be moles. So 1 mole of O2 to 2 moles of MgO. So moles of O2 cancel moles of O2. That leaves me with moles of MgO. 7.5 times 2 is going to be 15 moles of MgO. So if I react 7.5 moles of oxygen, I have to assume in my reaction, the reaction requires both magnesium and oxygen to be present. If the 7.5 moles of oxygen are going to react, I have to assume that the magnesium's there too. It's not mentioned, but the reaction can't happen if both of them aren't there. So I'm assuming, okay, there's plenty of magnesium there. I'm going to use up all my oxygen. How much MgO will be formed? And 15 moles is the answer, okay? So then I can look at the next question, which is basically the same idea, but this time the wording of the question is exactly the same, except I switched out moles and I put grams in instead. So now I'm going to start with 7.5 grams of O2, and I'm going for the grams of MgO. If you look at the question though, I mean it's almost identical, except I just changed moles and moles to grams and grams. Now, that's a pretty key change, because if I look back at my mole map, the first problem I just did, I was going from moles of oxygen to moles of magnesium oxide. That was just I only moved 1 spot, so that was a 1 conversion problem. Very quick and easy problem, because I only had to move 1 spot over. But this new problem we're doing, I'm starting with the grams of oxygen, and I'm going for the grams of magnesium oxide. So whatever I'm starting with is considered compound A. Whatever I'm finishing with is compound B. And if I want to go from the grams, which is the mass of the starting material, to the grams of the product, which is the mass of B, to get from here to here, I have to move 1, 2, 3 steps over. Well, each step that I move is going to correspond to a conversion. So this is going to be a 3-step problem. This is probably the most common calculation that you're going to do in 1211. Over and over and over again, we're going to have problems where we start with a certain number of grams of reactant and we want to know how many grams of product are going to be formed. It's always going to be a 3-step problem. It's always going to set up the same way. To go from the grams to the moles of the reactant, I'm going to use the molecular weight. Then to go from the moles of the reactant to the moles of the product, I'm going to use the ratio from the balanced equation. And then to go from the moles of the product to the grams of the product, I'm going to use this molecular weight. Just remember, this is the molecular weight of the reactant. This is the molecular weight of the product. Now notice I'm not going down to the number of particles, because when we're learning what moles are, it's very important to kind of recognize Avogadro's number connects the moles of the compound to the number of particles. But really in a lab setting, when we're doing experiments, kind of hands-on ourselves, rarely are we worried about how many molecules there are. It's more about this top row going across. When we do a reaction and we want to know, okay, how much product am I going to end up with? That's going to be called the theoretical yield of a reaction. That's a calculation that we're going to do over and over and over again. So that top row is really what you want to focus on, probably 90% of your effort. All right, so let's go back and finish our problem that we had. So I'm doing the same reaction, but this time I'm going from 7.5 grams of O2 to the grams of MgO. We just said that's going to be a 3-step calculation. So I'm going to go ahead and set my 3 conversions up. The first conversion is going to use the molecular weight. The second one's going to be a ratio from the balanced equation. The third one's going to be a molecular weight. It's a pattern. Make sure you learn the pattern. So the first step, I'm going to use the molecular weight of O2. 16 times 2 is 32. So that means there's 32 grams of oxygen in 1 mole. That's going to change grams to moles. So right now, after that first step, I have the moles of compound A, which is my O2. Then I want to do the ratio, and it's going to be the magnesium oxide on top and the O2 on the bottom. So the ratio is always going to be B over A for my mole map. The one I'm starting with goes in the bottom, the one I'm finishing with goes in the top, okay? And I look at my ratio from the balanced equation, 1 O2 reacts to give 2 MgOs. And then finally, my last one, I've now converted over into magnesium oxide. My oxygen has canceled out. So now the molecular weight is magnesium oxide. Well, that's 24.3 plus 16 is 40.3. This time I want moles to go away, so 1 mole of magnesium oxide weighs 40.3 grams. So if I do that calculation, it's going to be 7.5 divided by 32 times 2 times 40.3. And I get 18.9 as my answer. And actually, if I want 2 sig figs, I probably should say 19 grams of MgO. All right, so if I'm doing a mole-to-mole calculation, that's just a 1-step quick one. But if I do the same thing, but it's grams to grams, it becomes a 3-step calculation. Make sure you get this down. It's probably the most important thing we've done so far in this chapter. So, we have another problem. I have an equation. Of course, on a test, I might give you the equation either like this, or I might give it to you in words. You have to be able to write out all the formulas. Then you have to balance the equation, which there's our coefficients. It's 1,666. So then, finally, the question itself, I want to calculate the moles of CO2 that come from the grams of glucose. So I'm going from the grams of this compound, that's going to be grams of A, to the moles of CO2. So I'm going on my mole map from grams of A to moles of B. And B is always just another compound. So specifically, when we look at our mole map, we kind of have to decide on all these problems. You have to decide, okay, how many steps do I need to do? So I'm starting with the grams of glucose right here. mass of A, and I'm going for the moles of something else, moles of B. So to get from there to there, that's just 2 steps. So I know when I work this problem, I should be doing 2 conversions from the original number. Okay, so go ahead and try to do that yourself. Get it done while I write stuff down on my board. All right, so this problem is going to look very much like the one we just did a minute ago. I'm going to start with 10 grams of C6H12O6. I'm going for the moles of CO2. The first step from grams, I always have to go to moles. You'd have to add up the molecular weight of glucose. You should come up with about 180. So it's going to be 180 grams per mole. Then I need the ratio. Specifically, glucose has a 1 in front, CO2 has a 6. So it's going to be 1 glucose in the bottom to 6 CO2s in the top. That gets me my moles of CO2. I'm done. So 10 divided by 180 times 6 should come out to be 0.333, I think is the answer. Okay? Keep going, we might be able to get one more done on this video. So, what mass of magnesium oxide is produced by burning 2.43 grams of magnesium in the presence of oxygen? Go ahead and see if you can solve that. And again, I'll set it up on the board. Now, once again, if it's a grams to grams problem, it's going to be 3 steps. The setup is always going to be the molecular weight of the first one at the bottom, the ratio of B over A in the middle, and then the molecular weight of the second compound in the top. That's what it's going to look like. So it's going to be 2.43 grams of Mg, 1 mole. 24.3 grams is the atomic weight of magnesium. Then the ratio and the balanced equation, we've seen this reaction before, is 2 MgOs in the product and 2 Mgs in the reactant side. And then finally, the molecular weight of MgO is 40.3 grams to 1 mole. So if you do all that, I think that should work out to be 4.03 grams of MgO. All right, so then our next topic that we might get to introduce a little bit, percent yield. So when we do a reaction like the one we just talked about, we said that if we react 2.43 grams of magnesium, the amount of magnesium oxide that we should get would be 4.03 grams. That value is that's the perfect value. If you do the reaction and everything goes exactly the way it's supposed to, and every molecule or atom of the reactants gets completely turned into products, the best you could do is 4.03 grams, okay? That value is a theoretical value. In real life, you're never going to get that much, okay? You're never going to make the full amount that you expect to. So we have 3 terms that we have. The theoretical yield is what we should get. That's what we just calculated. If we do the experiment and weigh our product at the end, that's going to be what we call the actual yield, meaning in real life, if you do it, you're going to get less than the theoretical yield, so that's actual. And then if you actually want to kind of assess how well you did, you do the actual yield over the theoretical yield times 100 to get the percent yield, okay? And if you do a reaction and you get 95% yield, basically what you're saying is you got 95% of what you could have gotten. typically that's considered to be a pretty good yield. Some reactions, though, that are a little bit harder or don't work as well, sometimes you might do a reaction and only get 10% yield or 20% yield or something like that. And sometimes that means you did a bad job. Sometimes that might mean it's a really difficult reaction. Not every reaction works as well as others do. Okay? So it kind of depends on the situation, but every company, if they're trying to make, like if a pharmaceutical company is trying to make aspirin and they do a reaction, the higher their percent yield is, the more of their product they make, then the more money they're going to make off of the process. Okay? So, the amount that we expect, which is the theoretical yield, is based on the amount of starting material. Okay, so in the previous problem, the more magnesium we started with, the more product we would make. Okay? But if we want to do a better job, it doesn't necessarily mean always just put more reactant in, because when we want to assess how well we did, it's more about what percentage we can get. Okay? So to do a better job doesn't mean just make all the numbers bigger. It means to be more efficient in trying to make sure that everything we put in as a reactant, we want to make sure it all gets converted to the products the best that we can. And here's our equation, percent yield. The top is what we call the actual yield. The bottom is what we call the theoretical yield, and then times 100. So I'm going to have to cut it off. We'll do this problem on the next video.